Rectangular Approximation Method. Approximating area using the Rectangular Approximation Method. Suppose we want to calculate the area under a curve and above the x-axis over an x interval. How do we find this exact area? So here's a graph of some curve. Let's call this function f of x. And so let's say we're interested in finding the area that's underneath this curve and above the x-axis over some x interval. So let's say the x interval from 0 to 6. So let's go ahead and highlight that region. So we're interested in finding this area here, which isn't a specific geometric shape that we have a known formula for. It's not a perfect circle, triangle, rectangle. So what we can do is we can approximate this area using rectangles because we know the formula for the area of a rectangle. And to make things easier, what we're going to do is we will use rectangles of equal width. So every rectangle will have the same width. So I chose this interval here from 0 to 6. So what we can do is use, let's say, 3 rectangles of equal width, meaning that each of the rectangles is going to have this width of 2 units. So if I have this width of 2 units here, so this first rectangle is going to have a width of 2 units. I'll make it really bold so we can see it. And so then now I need the height of this rectangle. And so I'm going to have some different options. I can choose to define the height. So remember that I'm using these rectangles to approximate the area here. So let's go ahead and choose to use the right side x value to find a corresponding y value. So right at the x value 2, I'm going to go up, I'm going to find the function up there, and that's going to define the height of this rectangle on the interval from 0 to 2. So there's one rectangle. So this first rectangle to approximate the area is a little bit of an over approximation because I would be collecting this extra area that I don't actually want. So now let's go ahead and construct a second rectangle with the same width. So let's say between 2 and 4 because that's a width of 2. And I'll go ahead and stick to using the right side of the interval to find the height. So I'm going to find the y value of the function at 4. So that's going to be right about here. And that's going to define the height over the next interval. So that length from 2 to 4. So here's my second rectangle. And the second rectangle is an under approximation for this middle portion here because I have all this extra part. And then my last rectangle with a width of 2 is going to extend from 4 to 6, and again I will use the right hand side to define the height. And so that means that this rectangle is going to also be an over approximation. It's got a little messy here because I have all this extra area that I'm collecting with this third rectangle. But this is an approximation for that actual area under the curve and above the x-axis over the interval from 0 to 6. So in this section, we're going to go ahead and sort of play around with using rectangles to approximate area. And we're going to change the number of rectangles, which will change the width of the rectangle, and we'll choose some different values to define the heights for different examples. In this example, we want to find the area under the graph of f of x shown and above the x-axis on the interval from 0 to 12. Let's start by shading in the region that we want to find. Alright, so here's the area that we're actually interested in finding. And in part A, we're going to approximate the area using 4 rectangles of equal width and right endpoints to define the height. Or, for short, we want to find r sub 4. Alright, so the interval that we are interested in extends from x equals 0 to x equals 12. So if I want 4 rectangles of equal width, in order to find the width of each rectangle, I'm going to have to go ahead and take 12 divided by 4. So the width of each rectangle is 3, which is a calculation you can do in your head. And so the first width is going to extend from 0 to 3. And the next one is going to extend from 3 to 6. And then we're going to have one from 6 to 9. And then the last one will be from 9 to 12. So those are the widths of each rectangle. And then I'm told to define the height using right endpoints. So over the first interval, the right-hand side corresponds to the x value 3. So to find the height of that first rectangle, I'm going to go to the right side, 3, and find the function. So the function is located at the x value 3 at the y value 5. So that's going to define the height of my first rectangle. So my first rectangle is going to have a base of 3 and a height of 5. So far, what I have here is that R4 is equal to a base of 3 times a height of 5. So we can calculate the area of this first rectangle using the formula base times height. Now we're going to move on to the next rectangle. That extends from x equals 3 to x equals 6. 6 is the right side of that interval, so I'm going to define the height at the x value 6, which is, I missed a little bit, going to take me up to the y value 10. And so that's going to define my height. So my next rectangle has a base of 3 and a height of 10. So we're going to add 3 times 10, and then we'll move on to the third width extending from 6 to 9. The right side of that interval is 9. That's going to define the height. So I find the y value at the x value 9, which corresponds to 1. And so over that entire interval, the height will be 1. So the right side defines the height over the entire interval. So that next rectangle has an area of 3 times 1. And finally, the last rectangle extends from the x value 9 to 12. 12 is on the right-hand side there. If I use that to define the height at 12 is 8. So over that entire interval, I'm going to have a height of 8. So the area of that last rectangle is 3 times 8. So now R4 is simply adding up all of these values. So I can now go ahead and say 3 times 5 is 15, 3 times 10 is 30, 3 times 1 is 3, 3 times 8, is 24. So I have 45, 48, and 24 is 72. So an approximation for the area under the curve and above the x-axis on 0 to 12 using right endpoints and 4 rectangles is 72. Now, is it a good approximation? Well, if I look at the rectangles, I can see the first two are over approximations. They put a little too much. The second one is definitely, or the third one, excuse me, is an under approximation. And then the fourth one is definitely an over approximation. So it's not great, but it is an approximation. In part B, we want to approximate the area using 3 rectangles of equal width and left endpoints to define the height, or L3. So this time, if we're only using 3 rectangles and we want to have equal width, then that interval from 0 to 12 is going to be split into 3 equal parts, so each one is going to have a width of 4. So my first interval is going to extend from 0 to 4. My next interval is going to extend from 4 to 8, and my last interval will extend from 8 to 12. So to go ahead and find L3 over the first interval here, so the base is 4, and if the left endpoint defines the height, there isn't a height at all. So at the x value 0, the y value is also 0. So we have 4 times 0, so nothing is contributed in terms of an approximation here from that first interval. Moving on to the next interval from 4 to 8, the left-hand side corresponds to the x value 4, so that's what we'll use to define the height. So we'll go up, we'll find the function, which is up here at the y value 6. So 6 will define the height over that entire interval from 4 to 8. So my rectangle there has a base of 4 and a height of 6. And the last rectangle here, the left side corresponds to the x value 8. So I'm going to go ahead and find the function's output, the y value at the x value 8, which is also 6 again. So that's going to define the height over that last interval from 8 to 12. So that last rectangle also has a base of 4 and a height of 6. So now notice we can do each computation individually and add it together like the previous example, but we should also observe that because the width is the same in each rectangle, what we are going to be able to do is we are going to be able to factor that out and then simply add up the heights. So 4 times the quantity 0 plus 6 plus 6. So that's going to be 4 times 12, which is 48. Not that that computation was hard to do without doing that, but just to kind of show that is something we will be able to do every time if we are using equal widths. And in part C, we're going to approximate the area one last time using two rectangles of equal width and midpoints to define the height, or M2. So if the interval is from 0 to 12, we need to divide 12 into two equal parts, which means the width of each one is 6. So our first interval will extend from 0 to 6. Our second interval will extend from 6 to 12. Now this time we want to find M2, so we want to use midpoint to define the height. Now over the first interval from 0 to 6, the midpoint value, halfway, is the x value 3. So at the x value 3, that's where I'm going to go up and find the height there, find the output of the function, which happens to be a y value of 5. So that's my height over the entire interval from 0 to 6. So I like to use kind of a dotted line there to find the height, since that isn't one of the sides of the rectangle. It's just kind of right down the middle. And so the sides of the rectangle I will fill in with solid lines here. So here's my first rectangle from M2. It has a base of 6 and a height of 5. So 6 times 5. And for my next rectangle, between 6 and 12, the halfway point is 9. So at the x value 9, I'm going to go up and find the function to find the height over that interval, and that's at the y value 1. So my next rectangle has a base of 6 and a height of 1. So I'm going to say plus 6 times 1. And we'll just multiply these out. 6 times 5 is 30. 6 times 1 is 6. So an approximation is 36. In this example, I'm given the equation y equals x squared plus 3 on the closed interval from 0 to 8. And suppose we want to find the area under the curve and above the x-axis. So let's start by highlighting what area we're trying to find. So now here I have highlighted the area under the graph of y equals x squared plus 3 and above the x-axis between the x value 0 and the x value 8. And this is not a nice geometric shape where I have an area formula for it. So in part A, we're going to use rectangles, specifically two rectangles of equal width with height defined by the left endpoint, or we're going to find L2. So since we're going to have two rectangles of equal width over the interval from 0 to 8, I'm going to go ahead and calculate my delta x. So delta x, the width of each rectangle, is found by doing b minus a. Well, a is 0 and b is 8. So we're going to have 8 minus 0 divided by n, which is the number of rectangles. So in part A, the number of rectangles is 2. So 8 minus 0 over 2 is 4. The width of each rectangle is 4. So my first rectangle's width is going to extend from 0 to 4 on the x-axis. And now we're told that the height is defined by the left endpoint. So the left side of this interval is at x equals 0. So I'm going to go find the function. The height for that rectangle is found by going to the x value 0 and then going to that corresponding y value up there. And that's the height over that entire interval from 0 to 4. So we want to find the area of that rectangle. So L2 so far is going to be 4, the width, times the height. Well, the height, we sketch the rectangle, but we can't really see exactly what that value is from the graph of the y value at 0. So how am I going to get that height? Well, I have the equation x squared plus 3. So I would plug 0 into the function. So we're going to calculate y of 0. So we're going to have 4 times y of 0 plus, now the next rectangle will extend from the x value 4 to the x value 8. So that is a width of 4. And then again, the left side defines the height. So I'm going to go to 4, which is on the left side of the interval from 4 to 8. I'm going to go up and find the function. Try to draw a straight line straight up there. I'm going to find the function that defines my height over that entire interval. So I want to find the area of that next rectangle, which has, again, a width of 4, but this time the height is found by substituting 4 into the function. So we can't really, again, eyeball it here from the graph, so we would calculate it by plugging 4 into y, so y of 4. All right, well, notice that both of these have in common that factor of 4. So we can factor the 4 out, and we're doing 4 times y of 0 plus y of 4. So we have 4 times, well, y of 0, if I plug 0 into x squared plus 3, that's just going to give me 3. And y of 4 is going to give me 4 squared plus 3. So I have 4 times, inside here, I'm going to end up with 4 squared is 16, and then I'm adding 6 to it, so a total of 22. So 4 times 22 is equal to 88. So this is an approximation of the area that's under x squared plus 3 between 0 and 8. But it's clearly an under approximation because I'm missing all of this area. There's these gaps that are happening because my rectangles are both under the curve. So when the heights of the rectangles are found or are determined by using the minimum function value on each subinterval, by using the minimum function value. So over the interval from 0 to 4, the smallest value was that left side, and then between 4 and 8, the smallest value was again that left side. So if we always use the minimum function value over each subinterval, our area estimation is what we call a lower sum. And it's always going to underestimate the actual or true area under the curve because you're using the smallest possible value over that interval. So we're calling it a lower sum, and it will always be under the actual or true area under the curve. For part B, we have the same function, but now we're going to use 4 rectangles of equal width with height defined by the right endpoint, or this time we're going to find R4. So our delta x, our width of each rectangle, is going to be different because we have a different number of rectangles. So we're going to calculate delta x this time as still 8 minus 0, but this time divided by 4. 4 is the number of rectangles. So the width of each rectangle is 2. So our first rectangle will extend from 0 to 2 on the x-axis, and the right side defines the height. So we are going to end up plugging 2 into our function to find the height of the first rectangle. And I'm going to keep sketching all the rectangles. Our next rectangle is going to extend from 2 to 4. And the right side of that interval will define the height over that entire interval. Then the interval from 4 to 6 on the x-axis. 6 is the right side of that interval, so that will define the height over that interval from 4 to 6. And finally, from 6 to 8, the right side will define the height, which would be that 8, over that interval from 6 to 8. So we have our 4 rectangles sketched, and now let's do our computation. So to calculate R4, well, we're going to have to multiply the width times the height, the width times the height, the width times the height, and the width times the height, but the width is the same in every rectangle. So I'm going to have that width 2 just stay on the outside because it's in common, it's a factor of all of them. And so I'll keep the 2 on the outside of the set of parentheses where I'm just going to add up all of the heights. So the first height was defined by the right side of the interval at 2. So we're going to have to plug 2 into our function, so y of 2, then plus y of 4, plus y of 6, and plus y of 8. I'm going to have to add up 4 heights here, and they're all again defined by the right side of each interval. So now I'm going to substitute each of these values into my function to actually find what that height is. I just sort of approximated it when I drew my graph, but now I want to plug them all in. So 2 squared plus 3, 4 squared plus 3, 6 squared plus 3, and 8 squared plus 3. And then we'll compute each of those. And then we'll add up each of those values. So we'll have 2 times 132, which is 264. So this is another approximation for the exact area under the curve, but we can see that this is going to be an over approximation. We have all this extra area that we're accumulating here. So notice this time when the heights of the rectangle are determined by the maximum value, the maximum function value on each subinterval. So between 0 and 2, we picked the highest output, 2 to 4, the highest output over each interval. Our area estimation is always going to be an upper sum. That's what we call it, an upper sum if we choose the biggest output over each subinterval. And that's always going to overestimate the true area under the curve. And for part C, we're going to use 4 rectangles again of equal width, but this time the heights are going to be defined by the midpoint of the interval, or for short, we're going to find m sub 4. So we already calculated delta x when there were 4 rectangles. Delta x was equal to 2. So what we're going to do is we're going to draw the first width that extends from 0 to 2. But now the midpoint of that interval, so halfway between 0 and 2 is 1, the midpoint is going to define the height. So I'm going to find the height of the function at 1. And that's going to define the height over that interval from 0 to 2. Then from 2 to 4, I have my next width, and the midpoint between 2 and 4 is 3, so the height at 3 is going to define my height over that entire interval from 2 to 4. And then between 4 and 6, the midpoint is 5, so 5 is going to define the height. So over that interval from 4 to 6, that height is going to be defined by plugging 5 into the function. And finally, between 6 and 8, the midpoint is going to be defined by the height at 7. 7 is halfway between 6 and 8, so that's going to define my height over that last interval. Okay, so now let's do the computation. So here, to find M4, well again, the width is in common in every single one of these rectangles. The width is 2. So we'll go ahead and factor that out of each of them. So we'll keep the 2 on the outside. And now we're finding the heights at those midpoint values. So we're finding y of 1 and y of 3 and y of 5 and y of 7, and we're adding all of those together. And so we're going to substitute each of those x values into our y function. And then we'll go ahead and calculate each of those values. And now if we add up the quantity in parentheses, we're going to have 2 times 96, which is 192. And so on this one, notice that for each rectangular approximation, I have a little bit over and a little bit under of the area that I'm actually trying to find. So here we can't say with certainty whether we have an over approximation or an under approximation. We would need to clearly have all of the rectangles below the curve or all of the rectangles above with excess to say it's an over approximation. So here we couldn't say for certainty whether it's an over or under approximation, but it does look like a pretty good approximation. Sample readings for the speed of a car are captured every 5 seconds over a 30-second interval. So here's a table of values. Time is in seconds every 5 seconds. We can see the speed in feet per second. So at 0 seconds, the car was going 25 feet per second. At 5 seconds, the car was going 31 feet per second, and so on. Part A, find an upper sum estimate for the distance traveled by the car during the 30-second interval. So here we are trying to estimate the distance traveled, and what that's really asking us to do is approximate the area under the velocity function over the interval from 0 to 30, and the way we approximate area is using rectangles. So our first rectangle is going to extend from 0 to 5 seconds. So the width of the rectangle is going to end up being 5. And the units here are in seconds, 5 seconds. So we're going to have 5 seconds times, well, for the height, we have two choices. We have 25 and 31. But we're told to find an upper sum estimate. So we're going to look at the two outputs, which are the possibilities for the height of the rectangle, and pick the larger one, because for upper sums, we need the maximum. And so our only choice here, the bigger of the two, is 31. So 31, and then the units there are feet per second. So notice what's going to happen is that the units of seconds are going to cancel out. And so we're going to be left with just units that are in feet, which makes sense since this is an estimate for distance traveled. So now let's do the remaining computations, and this time I'll leave off the units. So the next rectangle will extend from 5 to 10 seconds. Well, that's still 5 seconds total. So we're going to have 5 times, well, between 31 and 35, the two possible heights or outputs, 35 is the biggest. So 5 times 35 plus the next width is 5 times a height of 43. Between 35 and 43, 43 is bigger. Plus between 15 and 20, that's 5 seconds. So we have 5 times 47, the bigger output is 47, between 43 and 47, plus between 20 and 25 is 5 seconds, and between 47 and 46, 47 is the bigger one. So we have 47, and then between 25 and 30, that distance is 5 seconds, and between 46 and 48, 48 is bigger, so 5 times 48. And so now this is just a lot of multiplying and then adding together. So we can either multiply each quantity and add them, or recognize they all have a 5 in common and then add all of those heights together. Either way, we'll get the same answer, which is 1,255 with the units of feet. Now for part B, we want to find a lower sum estimate for the distance traveled during the 30-second interval of time. So a lower sum estimate, we're still going to use that 5-second interval each time, but now as I look at the two outputs, I'm going to pick the minimum or the smaller of the two. So I'm going to have 5 times 25 plus here 5 times 31 plus 5 times 35 plus 5 times 43 plus 5 times 46 and then the last 5 is also multiplied by 46. And again, if I perform all of this multiplication and addition, I'm going to end up with 1,130 feet. Now in our last part, part C, find an estimate for the distance traveled by the car during the 30-second interval using M3. So I want to use midpoints and 3 rectangles. Well, our delta t in this case, since t is the input variable, the width of each rectangle is 30 minus 0 over 3. So the width of each rectangle is 10. And that makes sense, right? A 30-second interval divided into 3 equal parts is 10 seconds each. So our first interval will extend from 0 to 10 seconds, and the midpoint defines the height. So the midpoint there is 5, but the height is 31. So we don't want to use 5. That's the middle value that is used to find the output, the height of 31. So we're going to have 10 times 31, plus the next rectangle will extend from 10 to 20. So that's still 10 for a width. And then the midpoint of 15 defines the height. So the height at 15 is 43. So we're going to have 10 times 43. And then finally, between 20 and 30, that's also 10. So each of these was 10 seconds. And the height at the midpoint, 25, is 46. So we have 10 times 46. And the units there are going to be in feet. So my final answer is 1,200 feet on this one. Because again, each time we were multiplying seconds times feet per second, seconds will cancel to just give us feet. All right, let's go ahead and look over some terminology now. So we have the A is going to be the left endpoint of the interval A to B. So matching it up with the graphs that we have here. So A is the left endpoint of each of the intervals, and B is the right point of each of the intervals. Now, we call N, capital N, the number of subintervals A to B, or the number of rectangles that we are creating. So in this example, we would have that N is equal to 7. Here, we would have that N is equal to 9. So there are 9 equal subintervals. And then here, we have N is equal to 3. So all of these are equal subintervals. And we call delta x the width of each subinterval or rectangle. So there is a formula for finding delta x. We would subtract b minus a, so we would subtract the end point of the interval with the starting point and divide by n, the number of rectangles, and that will find us our delta x. So in that last example, we were able to think about the interval from 0 to 2, and we want 4 intervals, so that's going to give us 0.5. So essentially that's what this formula here is. So what is delta x? That is the width. So each of these are delta x. So over here, these smaller widths are delta x. Here, these are my delta x's. So the widths of each of my rectangles. And so we did each of these types of approximations where we used over each interval the left side. You can see the arrow pointing to the left side of the interval. We did the right side of the interval as well. And then we also did the middle of the subinterval to define the height of the rectangle. Now we're going to get a little bit more technical and think about the nth left endpoint approximation, L sub n. So over each subinterval, we construct the rectangle whose height is the value of f of x at the left endpoint on the subinterval. So we did an example of this, but it's formally coming from this definition here, which can be a little bit hard to understand, so we're going to go ahead and label up our graph to make sure we understand the notation. So here I can see that my left endpoint is A, my right endpoint is B. Each of these widths are generically delta x. I have my function f of x. Now here, this first point is generically going to be represented by the value of A, whatever it is, plus this width delta x. So this first point, this first x value, would be A plus 1 copy of delta x. And that means that the height of the rectangle there is going to end up looking like, so this coordinate point up here is a plus delta x, and then f of a plus delta x. And if I move on to the next subdivision, it's going to be a plus 2 copies of delta x for this second point right here, because now from the starting value a, I've added 2 copies of delta x. So then this height here is going to end up looking like a plus 2 delta x, and then f of a plus 2 delta x. And we would obviously continue on in this fashion. So now going back and trying to make sense of this, L sub n is equal to the first rectangle's area, delta x times f of a. So that's the width, delta x, and the leftmost endpoint would be a, so delta x f of a, plus the next rectangle is delta x again, the width of the next rectangle is the same, and then the height is f of a plus delta x, as we showed here that was the height. So you can see that all of these have in common that delta x, that is the width, and then we have each of the heights. Now the last height is going to be at f of a plus n minus 1 delta x. So over here, this last height, this last leftmost endpoint height, is going to be represented by, so generically this value is a plus and then n minus 1, because remember n is the number of rectangles, so n minus 1 copies of delta x. So that makes its height f of a plus n minus 1 delta x. That's the last height we're going to use. So we're not going to use b because that would be a right endpoint, and we're using left endpoints only. So that's where we stop. Now, since all of these have delta x in common, we can go ahead and factor it out, which we did on a few of our examples. So delta x is pulled outside, and then we have left just the heights added together. Now, whenever we're adding a bunch of terms together here, like this in this type of pattern, we can use summation notation. So the delta x has since been factored out, is written in the front, and the function values that we're going to look like or use inside the summation are f of a plus I delta x. So I is the indexing variable, that's what's changing. So the first value of I is going to end up being 0 because there is no delta x in the first function height. It's just f of a. So if I substitute in 0 first for I, the delta x is gone. And the next value I'm going to substitute in is 1, and then 2, all the way up to the last indexing value is n minus 1, depending on the given n. Now we also have a right endpoint approximation Rn and a midpoint approximation Mn with their own respective summation notation formulas. And I just want to point out the difference. So I still have delta x because that width is still the same. And what's inside the summation, f of a plus I delta x, that's the same as well. So what makes this different, what makes it a right endpoint approximation, is our indexing values. So for a right-hand approximation, we're going to start at 1 instead of at 0, and we're going to end at n instead of n minus 1, because we're skipping over 0 because we're going to skip over a, that leftmost point. We need to just jump to the right endpoint over the first subinterval. And for the midpoint approximation, again, we can still factor out the delta x. What makes this one different here is this I minus 1/2 delta x. So this is what's going to get us to that halfway point over the subinterval. Now, the reason why we're taking some time to go over this is because we're going to be looking at a formal definition in a bit that involves summation notations that look like these. So the more you can wrap your mind around these concrete ideas that apply to the example we looked at earlier, the easier it is going to be to understand this summation notation going forward.